All right, we have something a little different than the last couple discussions. Something new, something that I think is very exciting and interesting, and will be discussed in likely more than one video. And that is a recent paper that has been put out that included me as one of the authors. And it's about a software package called QuantumCircuitOpt, an open source framework for provably optimally quantum circuit design. So we're going to go over today the sort of the basic usage of QuantumCircuitOpt and just the incentivization and stuff like that. So in terms of the problem setting, first we need to motivate what's going on here. Basically, the problem we're trying to solve is you have some circuit, right? And before I say anything, I should note this was submitted to a conference, and you can see the video that the first author put out for the conference. I'll link that. But this is sort of more of a user guide rather than a sort of theoretical discussion. Anyway, you write your nice, cool little circuit, right? You have your qubits. Here, you do your cool, whatever sort of circuit you want to do. And then, you have this circuit, right? And now you're like, okay, I would like to, make this a real world thing. I don't just want to live in the simulator land. Let's run this on hardware. Maybe you have access to company hardware. Maybe you have access to Google's hardware. Maybe you're paying for hardware through, AWS services or through IonQ or Rigetti or something. Or maybe you want to use the free services that IBM provides. To the best of my knowledge, IBM is the only company that offers free access to quantum computers without any sort of like application process. I think you can get access to Google's hardware, but you have to like apply and have a professor and a whole research project. So it's free, but there's a lot of prerequisites. Whereas I think I'm happy to be corrected on this, that IBM is the only one that says you can just put down a Gmail account and you can submit quantum hardware. So now let's suppose that you want to run this on one of the IBM systems. Well, that's great. Let's look up IBM Quantum Systems. Let's pick one. So we go over here. This is really okay. Why can I not just get there? Oh, here we go. This is what I want. And then we want to see their services. All right, so these are a bunch of programs that you can just run, but we see all of these systems. All right, let's go down to, I don't know what exploratory, pre-production. All right, let's say this right here was a 2-qubit circuit that I just drew. So let's look at, we need a 2-qubit system. Manila, that looks like it has big numbers right here. All right, so here we have Manila. You can see two things of note here. One, controlled not RZ, square root of x, and x are all gates, but this is not a native gate. This is not a native gate. This is not a native gate. Actually, RZ is, so I guess this is RZ of, pi. But these are the rest of them. This is not a native gate. These are non-native gates. So we have to convert these somehow into one of these gates or some combination of them. Additionally, in this case, it's a 2-qubit example, but suppose we have a third qubit here. Now we do this, controlled x. Well, there's a qubit here and there's a qubit here, but there's no connection between them. Superconducting qubits do not usually have all-to-all connections. That's something that IonQ, for example, might have because the you can just move the little trapped ions around with lasers, whereas superconducting qubits are sort of static, so their topology is defined. Okay, well now I have to convert this circuit into this topology and the native gates, and that's a non-trivial problem. And so this is where our idea comes in, which is circuit decompositions. And this is not a new sort of field of research. Lots and lots of people have been looking into how do we convert these circuits into the basis gates of any given hardware, and different hardware will have different basis gates. So if I do like Rigetti basis gates, we'll see. All right, see, so for example, Rigetti has RX, RZ, CZ, and XY, which is a parameterized swap gate. So we have to do, we would have to convert even more of these. You know, CX isn't even a native gate here, so we'd have to do more. So in every case, right, it's different. And so in order to solve this problem, there's a variety of heuristics and techniques. You can look at existing sort of approaches. There's things called, I believe, CAC decompositions that can be used for these, which you can see are implemented in some packages already. And there's different ways to sort of decompose this, but the approach that's taken here by us is to reformat this problem into an optimization problem and then solve it using existing techniques. And so we can see here that how we formulate this is a mixed integer programming problem. So we have our objective, which is we're trying to find the most efficient representation. Obviously, you could do this out by hand, and I could do this in 1,000 gates or something, but then that's not very useful. We want to find the best decomposition because that's going to be the one that gives us the best results on hardware. And so if we formulate in this way, in this mixed integer programming way, we can not only get a good result, we can get the best result. Mixed integer programming, when it converges to a solution, unlike sort of these gradient-based approaches like neural networks and stuff, it'll give you a provably optimal solution. So anything that this problem formulation spits out as a solution is the optimal solution to that problem. There's nothing that you could do that would improve that solution according to your objective. Of course, you can have different objectives that might be competing, but when you specify that, this is the optimal solution to the mixed integer programming problem. So there's two main objectives that we're considering here, which is minimizing depth and minimizing C-naughts. Both of them are relevant. I'm mostly just going to be talking about the minimizing C-naughts, but you can just specify that in the program. So we're going to get into the program a little bit now. Now that we've motivated, okay, this is an important problem for not only for near-term hardware, but for the future too. We want the best solutions that we can have no matter what. Even on our current computers, right? If I could tell you I can get a 2% increase on this, transistor that's in every computer in the world, that's going to be a huge deal. So even if quantum computers become, fault tolerant and they're proliferated and there's millions of qubits, these optimization problems are still very important for these common subroutines. But they're even more important, arguably, for near-term hardware, which is so noisy that you absolutely need the best gate solutions that you possibly can have. So now you can see, for those of you familiar with mixed integer programming, this is just a standard, right? You're trying to minimize some objective, you're subject to some constraints, for example. We're trying to say, there's going to be a maximum depth, there's going to be conflicting, right? You can't have two gates at the same depth. There's all these sort of problem formulations to get it to fit into this. And the main tool that I'm going to be using is called Cplex. So this is a commercial mixed integer programming solver. There are open source ones like CBC. However, they are unfortunately much slower than Cplex and Gurobi, which are the two sort of state-of-the-art solvers. Cplex is put out by IBM and Gurobi is put out by, I think just Gurobi is the company as well. I don't know the history of this sort of integer programming, so I don't know why there's just so much better. Maybe just more money's been put into them, but both of them have academic licenses. That's what I didn't pay for them. You can get it if you're a student or a researcher or anything. They might even have versions that are open to the community. I don't know, but if you're a student or a researcher, you can easily get access to both Cplex and Gurobi. And even if you're not, you can there's probably also ways to get access. But it is unfortunate. I do like everything to be open source, but if you're doing mixed integer programming, like no matter what you're doing, no matter what field of research you're doing, you're going to be using these sort of commercial ones just because they're orders of magnitude better and faster than the open source competitors. Like a lot of code that might take 100 seconds to run with these will never basically finish with the open source ones, which is unfortunate, as I'm a big fan of open source work. But anyway, this is, by the way, all written in Julia, which is, for those of you unfamiliar, it's similar to these scientific computing languages, other scientific computing languages, and that's sort of its goal, is to be scientific computing. I'm not entirely sure of all the programming languages specific, but it's nice because there's speed advantages. There's some pre-compilation sort of work that Julia does that can make it a lot faster than Python, which is nice, but it still has a very Pythonic feel to it, which is good. So now we're going to be talking about, briefly, we're going to discuss the sort of math. And I'm not going to really mention it at all. I'm just going to say you can look at this paper, which of course I will link, and you can read it for yourself. This was this formulation was not, it's not my expertise, but it's still, I think, very understandable. Basically, what you're saying here is we're just discretizing the whole circuit. So, at a given depth, right, we have this is a variable, right, that can be filled with a given gate. And then at every possible combination, we have a variable that can be filled by a given gate, either the identity or one of our specified gates. And then you can generalize this into the sort of problem setting, right? We're trying to make sure that here we can see in equation 3b that using this example of basis gates, at this depth, there can only be one gate there. You can't have multiple gates occupying the same spot. And then we can do some techniques to formulate this into a different method that can make it a lot faster. And there's a lot of techniques to reduce the search space, because clearly you can see this is extremely, if we made this a really big depth, really large number of qubits, it very quickly gets extremely hard to solve. So we need to reduce the search space, and we can do that because obviously there's a lot of symmetries just even off the top of your head that you can look at, because we know that, for example, commuting gates, if you have, for example, I guess the example that comes into my top of the head doesn't really matter. Oh, for example, if you have x, I mean, that's just the identity there, but it doesn't matter what order you would apply them. So we don't need a search, or let's suppose, I'm trying to think right now at the top of my head of the two commuting gates. Anyway, I'm trying to think of the best example, and there's not one coming to my head. But commuting gates, right? You don't need to check both orders because they're the same either way. So you can eliminate all of those possible values that are the reverse of these commutators. You can also eliminate any gates that are their own adjoint, because if you have XX, right, that's just I. So you don't need, you can reduce that search space by saying, okay, I don't need XX anywhere because that's just going to be the identity. So basically, that's the sort of mathematical background. You can check it out more. So we can see we're just trying to minimize the depth here, the number of gates that we're applying. But I highly recommend for those of you interested in the actual sort of optimization background to check it out. But now we're just going to move into how do we actually use this package. So here we can see the home page for the package, and it is pretty easy. I always just clone the repo, basically use the nightly build, if you will, but you can just use Julia's package manager as well. But this is pretty much always what I do, just because I would often make commits to this repository, so I wanted to always be working with the most recent version. Also, you can see the video that the first author did at the conference, right? Oh, and there's an ad right here. If I do this, so you can see that you can watch this whole video. This has a lot more discussion of the sort of mathematical background here. There's a lot of information there that I didn't go over. So now we're going to just get into using it. There's a little information on this the GitHub page, but the main link is if you go here, go to the Quick Start Guide, go over here, and you can see there's lots of information here on how to use it, what to do, a bunch of gates, all the functions that exist. But basically what we're going to be going into is what you have to do to use it. So let's go into some code right now. We're going to look at the general format right here. Do that. Here we go. So this is just a simple decomposition right here. So we want to import our package. So we have this QC-opt that we're working with. We're using jump, which is basically a Julia interface for these mixed integer optimization problems. Just move that over. And then we're using Cplex as our optimizer. And that's pretty much straightforward. These are all we need when we're solving these problems. So now, right, we have some target sequence that we're trying to decompose. This can be a gate. This could also be it says target gate as the flag, but this is our circuit, right? Whatever it is, we want to decompose it into our native gates. So the main gist is we're going to specify our parameters, we're going to pass it to the model, and then we're going to run it. And that's going to give us the result. And that's all we have to do. So there's a number of things you can pass to the parameters. These are basically the required ones. So you have to say, how many qubits are you looking for? You have to say, what's the maximum depth? At some point, you have to cut it off. So this is kind of a heuristic. If you make it really deep, right, if you say the maximum depth is 100, it's going to have a huge search space, right, because it has to consider variables for that huge depth. So there is a little bit of heuristic here, but you can just make it big at first, and then the Cplex solver or the mixed integer programming solver will give you an upper bound that it decreases over time until it converges with the lower bound, and that when the upper bound and lower bound are the same, you converge to a solution. So you can also set this really high, wait for it to get down a little bit, then set it to that new lower upper bound, which will still improve the speed because your search space, even when the upper bound is decreased, is still very large. Then you have to specify, okay, what are these basis gates we're working with in this format? You can also do like products, tensor products, but this is the format for all the gates. Identity should always generally be included, unless your depth is exact, because you need that space. You specify your target that you want to decompose. The objective, you can either do minimize depth or minimize C-naughts. And then the decomposition decomposition type. You can get exact or you can do approximate. So in this case, we're doing exact, and I'll pretty much always be working with exact because there's a lot of approximate solvers over there, but the interesting things are the exact ones, right? So now we can, all we have to do is say, specify a dictionary that has the type. We can do compact formulation or what's called Ballas, I don't know how to say it, formulation. I'm not, the expert on which of those is better and when it's better, but you can try them both out. We want to visualize the result. Then we specify our optimizer. This is really easy. You just call jump and it handles everything. Optimizer with attributes, and then we run. We call it run QC model. We specify the parameters, we specify the optimizer, and we specify our options. And so if I run this right now, I will go over to my Julia console. Let me zoom in a little. I will do, in order to run things in this console, what I usually do is, this is test decomp.jl. You can just do include and then the file. So what's going on here? Well, we can see there's the information. So it detected that it's all real. All of these gates, right? There's no complex numbers in the gates. So we can simplify the problem because in order to represent complex numbers in this mixed integer formalism, we actually just double the size, right? We say, okay, rather than just having complex numbers, we have a second sort of set of variables that correspond to those complex numbers, but are real numbers themselves. And so if it detects that they're all real gates, then okay, it's easy. We don't need to worry about those complex numbers. There's 4 input gate pairs that commute, right? So H1, H2 commutes because it doesn't matter which order that you do it in. And then there's also 3 involuntary gates because every single one of these is its own inverse, right? H1 is the same. So now we see this is just a bunch of information about the Cplex solver. So this is going to be, I don't know what's everything that's going on here. This will always be there, but it's the Cplex doing this really fancy and really cool optimization thing. So it's eliminating things to make the problem simpler, and then now it runs it. And in this case, it's a very trivial problem because we're decomposing the CZ gate from H1, H2, C0, 1, 2. So it's a very simple decomposition. So it can't even measure how quickly it is. It's 0 seconds. So now we can see that, okay, this is the data we fed it. And then this is the result, H2, C0, 1, 2, H2. Oh, it actually does have the runtime down here, but that's because it includes this part, whereas this is just this section. And then this is just a result information so that you could work with it or something like that. But this is the pretty sort of results. This is what the minimum depth is and what the actual target is. And we can see with this result, I mean, in this case, it's not interesting, right? Everyone knows that CZ is we're just changing the basis. And so we have these Hadamards. But using these gate sets, you cannot get any better than this. This is the, provably optimal solution. So now we're going to get into a little more interesting things, which is we're going to be looking at rotation gates, and we're going to be doing some controlled rotation examples. This was one of my big changes to this was enabling all of these. Originally controlled rotations were not allowed, but I added all of these controlled rotations that you can now do very easily. So what we want to do, and this is completely tangential, but I always like to use QCOpt just to do like different things. If you just open up Julia, you can get all the gates really easily. And then like if you want to do, I wonder, what's this gate? If you're doing like Kronecker products, right, and you're like, okay, I have C0, 1, 2, C0, 2, 3, and then H gate on 4, like that's crazy. I don't want to do all the matrices and like NumPy and stuff. What you can do is you can do the, you can call this function called, let me double check. Let's see. It's called, here, let me go back to the actual Julia and I'll show you exactly what I mean. There we go. So if we want to, for example, let's say we just want to do some, okay. All right, so let's say we have our little, our gate, right? So we want to do C naught 1, 2, and then we want this to be, we have 4 qubits in our system, let's say. So that's our 16 by 16 matrix. All right, so then I wanted to do, okay, now we can do, all right, now let's do CZ on 3, 1, right? And then we have 4 qubits. And then it's really easy to just, you know, this is a big matrix, but maybe I'll do, make it a little easier to read. Note that the indexing starts at 1, not 0. So this is just very handy. It's not not the point of the package, but I just use it a lot for these handy. Very nice to have these built-in Kronecker products. Anyway, back to what I was actually talking about, which was this working with the discretization. So let's get rid of these comments. We already know them. So now let's take, and I'm just going to make this up maybe real quick. Let's look at some native gates. Let's see. This is going to be sort of ad hoc, but I think it's going to be interesting. All right, so let's IonQ native gates. Let's just look at, I remember they're on, okay, so here are some native gates for IonQ's hardware. So let's decompose this Molmor-Sorensen gate. So we can run it on other hardware maybe. So if we go over here, so now rather than having an actual gate that we're specifying, we need to provide a matrix because this is not the built-in. So the way we do this, we say it's an array. We're specifying the data type here, and then it's a 2 by 2 array in this case. Well, I should say it's a 2-dimensional matrix. And then we have our gate. I can do 1 over square root of 2 times this, which is this 1, 0, 0, negative I, negative j. I'm trying to remember now. I'm not extensively familiar with Julia, so I'm pretty sure you can just do negative I, and then we have our, then you do a colon. We have a colon, and then let's see, it's 0, 0, 1, negative I, 0, and then we have a colon, and then 0, negative I, 1, 0, then we have a colon, or semicolon, I guess, negative I, 0, 0, 1. All right. So now let's just see what happens if we do it. Let's just run this right now. First, let me make sure that this actually is correct. Oopsies. Function. Oh, I forgot to say every function needs end in Julia. That's just something to. Yeah, so it's not I. It must be J then. I always forget whether. Or is it? It might be. Yeah, I think it's. Okay, this is I should really have looked this up beforehand. I always forget what the imaginary term is in Julia. Okay. All right, now we have our it's implemented. It's just IM. I always forget that it's IM instead of I for imaginary. And now we try to do it, and you'll notice that it does not work because it's telling us, hey, all of your elementary gates don't have imaginary parts. So there's no way this is infeasible to begin with. So now let's just add a maybe an I swap gate as an example. Specified I swap gate does not exist. Oh, I forget every single one has a different capitalization for yeah. Okay, so now I'll clear this. All right, this is what we want. All right, so here's another valuable piece of information. I knew this wasn't going to work, but that's my point. So we specified the ISWAP gate. If you're curious, I'll show the code briefly. So you can see I just specified ISWAP to run. And so now what this says is that, okay, there are no results. This is an infeasible solution. So approved, this is a proof you can take it to the bank, you know, that you cannot use these gates and achieve a solution of this of less than or equal to that depth. So you can't do that. It's impossible. So now let's try to find a solution that does work. So the first thing that's probably going to be important is to realize, okay, this gate is a 2-qubit gate. So we're probably going to want our C0s. I don't know what the decomposition is off the top of my head of this gate. So let's add our C0s. There's definitely complex parts, so we'll add some gates, right? We want gates that have complex components. So what's an example of a gate that has a complex component? Well, we know that the S gate does, so let's just put S in. We'll do it on the first qubit and on the second qubit. And then let's do controlled unitary from the first to the second qubit. Now, however, this controlled unitary is unbounded right now. There's nothing, right? It's not a integer problem. It's a unbounded sort of problem. So we need to specify the discretizations of this unitary gate. So we're going to specify the 3 discretizations of these gates. So we'll do maybe 3 pi over 4 over 4 pi over 4. Just copy this. Maybe I need to do 3 times pi. And this will be our discretization. Now let's see if this works. This should at least take longer. I don't know if this is actually going to converge. So now let's, need to make sure people can see this. All right, let's run our code now. Oh, I forgot to have put something in. This is probably to do with the discretization error I just did. So we can see right now. Oh, it's because here, this will just make it easier. If I do it this way, I will show you. All right, so the solution was simply that I wanted to write them out as a list. The colons were messing me up. So if you just change these to a list, we have our CU3 gates. I also added H1 and H2 gates just to see if the decomposition would work. And then we can go over and run it, which I actually already have it running. Oh, that's the wrong. Oh, I appear to have messed up. There we go. Now it is running. So we can see that at the beginning, there's a lot of elementary gate pairs that commute. It's doing a lot of optimization right now. Now we can see that for longer runs, this is what it's going to look like. It's going to find the, it's going to tell us, you know, it's searching. It's going to give us the lower bound, basically, the cuts it's done, and then eventually it will give us an upper bound. And then I'm just going to let this run briefly. It is computationally expensive. So I'll just let it run briefly. So after a little while, I did just cancel it because it wasn't converging, but we'll give an example that does converge to make this a little more interesting. So we can see now that we're going to look at the 2-qubit Rover diffusion gate, which is already built in. And so we can simply say, we can call the gate, and we're actually going to use the same depth here. We'll keep it at 4. Maybe we'll increase it to 5. We'll replace these with x's maybe. This is something, right, if you have no exact knowledge of the problem, right, it seems like I'm just guessing, which I am to a certain extent. But if you have more knowledge of the problem, then you can do things, right? If you have basis, right, I'm just picking gates basically out of a hat. But if you have basis gates, then, you know, you can have some hardware. So let's, we'll consider a sort of trivial example of that momentarily. You can see that I just changed the gates around a little bit, and then if we run the code, we can see that the result has yielded an example decomposition of the Rover diffusion gate. So this is basically the approach that we use for these decomposition problems. You can put in circuits, you can map other problems to them. So that's sort of an overview. I hope that was pretty comprehensive. This was pretty long. But if there's any questions on installation or usage or anything, you can, of course, comment. There's a GitHub page if there's like an issue or something. And then next time we'll be going over how you can actually get started with research and how you can contribute to this sort of stuff.